All right, so we're going to ask a random person, do they live in the city and favor combining city and county government? So C is that they live in the city, and F is that they favor combining city and county government. So let's notice that we have a contingency table, and those that are in event C are all the way across here, and those who are in event F are the blue ones going down. And we're going to answer these questions. So let's find the probability of C. Well, if we look all the way across, the total number that live in the city are 120 out of the 150 questioned. So that's 120 out of 150. And if we want to, we can make that into a decimal. 120 divided by 150 ends up being just plain old 0.8. All right, now we want the probability of C complement. Well, let's do it the easy way. Let's remember that C complement is 1 minus the probability of C. So 1 minus 0.8 is 0.2. All right, now I'm going to give myself some more room in here. I'm going to take 3 down to the bottom. I don't know why it does that. All right, so now we want the probability of F for number 3. So if we look at this column containing F, there are a total number of 100 people who favor combining city and county government out of the 150. So this is 100 over 150. And that's 0.6667. I'll call it 0.667. All right, now let's go to 4. We want the probability of C and F. Let's notice that C and F overlap right here at 80. So we want 80 out of the total 150. And again, let's just stick that into the calculator. And we get 0.533. All right, number 5, the probability of C or F. Now, just to get us used to using the formula, we could count up everything that is both C and F and add them up, but let's get used to using that formula. So the probability of C or F is the probability of C plus the probability of F minus the probability of both of them, of C and F. All right, so probability of C was 0.8. Probability of F was 0.666. 667, and the probability of both C and F was 0.533. And let's do that computation. And we get 0.934. All right, now let's go to 6, the probability of C given F. All right, so let's use the formula. The probability of C given F is the probability of C and F over the probability of the second one in the notation F. So the probability of C and F was number 4, 0.533. And then the probability of F was number 3's answer, 0.667. And if we put that in the calculator, we get 0.799. It's probably a solid 0.8 because we have rounded everything, but that's all right. We'll leave it as 0.799. All right, now number 7, let's do exactly the same thing. Let's do our formula again. So it's going to be the probability of C and F. But this time, on the bottom, it's the probability of C. So we'll have 0.533 still on the top. But let's go back and see what C was, 0.8. And if we put that in our calculator, we get 0.666. Again, probably a solid 2/3, but since we rounded, it's a little bit hard to tell. All right, now R, C, and F, dependent or independent. Now this is difficult to tell from a contingency table. So instead, let's use the definition of independence. All right, so our definition of independence says that the probability of C given F will be equal to the probability of C if they are independent. So let's see if that is true. Now, likewise, we could say the probability of F given C is equal to the probability of F. We can do either one to check for independence. All right, so the probability of C given F, we got that in number 6. And in number 6, it was 0.7999. And the probability of C, okay, is 0.8. Now, I did say that probably this is 0.8 because we've rounded. Things may not turn out perfectly. So this might be true. Just to be sure, let's do the other one. Let's see if the probability of F given C is equal to the probability of F. All right, so the probability of F given C was 7. It's 0.666. And again, I said that's probably 0.667 just because of rounding. And let's notice that the probability of C is 0.667. So we can very safely say that these are independent. They pass the rules for the definition of independent. So if something satisfies one of these conditions, it is independent. If this had not been equal, then it would have been dependent.